Boundary value problems with azimuthal symmetry, m equals 0 when m equals 0. The general solution is, see equation 5-27 that follows. Suppose we have v of theta on the surface of a sphere, radius a, and we want the potential inside. We can write, see equation 5-28. Consider a sphere centered at origin and cut by xy plane, with upper hemisphere positive v, and lower hemisphere at negative v potential. See equation 5-29 that follows, where only the script L odd terms are non-zero. To solve the integral, use 2 script L script plus 1 times p subscript L of x equals dp subscript L script plus 1 over dx minus dp subscript L script minus 1 over dx. See equation 5-30.
From Rodriguez formula p subscript L of x equals 1 over 2 to the script L th power script L script factorial times d to the script L th power over dx to the script L th power times x squared minus 1 to the script L th power. We have see equation 5-31 that follows. Thus, p sub n of 0 equals a sub 0 for even n, which is the m equals n over 2 term above. See equation 5-32. Thus, see the equation. And since 2 raised to the script L script minus 1 power times script L script minus 1 over 2 factorial equals 2 raised to script L script minus 1 over 2 power times script L script minus 1 factorial, we can simply further see equation 5-33 that follows.
So, see equation 5-34. Alternative solution to problem using Poisson's integral for sphere. See equation 5-35 that follows. Which for our potential? See equation 5-36. Note that cosine gamma equals cosine theta, the cosine of theta prime, plus sine theta, the sine of theta prime, the cosine of phi minus phi prime. For potential along z-axis theta equals 0 and cosine gamma equals the cosine of theta prime, for which the integral is solvable.
Consider outside first. See equation 5-37 that follows.
For the inside, the signs change in the 1/x terms. See equation 5-38, which simplifies to see equation 5-39 that follows. Note that they match at z equals a. Since the square root of a squared plus z squared almost equals a times 1 plus 1/2 times z over a squared, as z0 we can simplify to see equation 5-40, which is a dipole potential. Note that the center of the sphere mirrors the potential seen asymptotically, where a dipole is also seen asymptotically. This makes more sense. Returning to issue at hand, we now have a closed form for the potential on axis. See equation 5-41 that follows. And by matching this with phi of r, theta, equals the sum from script L script equals 0 to infinity of a subscript L r to the script LTH power plus b subscript L r raised to the negative, script L script plus 1, power times p subscript L of cosine theta where r equals z, cosine theta equals 1, we find an alternate way of obtaining the coefficients, with alternate expression see equation 5-42.
Thus see equation 5-43 that follows. Now that we've obtained some general forms of solution, let's consider the very important example of a point charge. What is the expansion for a potential involving 1 over the absolute value of x vector minus x vector prime ? Since there is azimuthal symmetry, the Laplace equation can be expanded as before, except at the point x vector minus x vector prime. Also, let x vector prime be along the z-axis. Let r sub is less than of, r sub is greater than, be the smaller, larger, of the absolute value of x vector and the absolute value of x vector prime, and let gamma be the angle between them, then, see the equation shown. Or see equation 5-44. Furthermore, let x vector also lie on the z-axis, cosine gamma equals 1 now.
See the following equations.
Either way we conclude. See equation 5-45 that follows. Now let's consider the potential due to a ring charge of radius a, height c equals b above xy plane, such that the distance from origin to ring is c at a declination angle alpha. See the equation.
The potential on the z-axis at distance r is then. See the equation shown.
For r is greater than c. See equation 5-46. For r is less than see equation 5-47 that follows.
The potential at any point in space is then see equation 5-48.
Example 5.1. Two concentric spheres have radii a, b with b greater than a, and are each divided into two hemispheres by the same horizontal plane. The upper hemisphere of the inner sphere and the lower hemisphere of the outer sphere are maintained at potential v. The other hemispheres are at zero potential. Determine the potential in the region A plus R equals B as a series in Legendre polynomials. Include terms up to L equals 4. Check your solution against known results in the limiting cases B infinity and is 0. With origin chosen at that of the concentric spheres, we clearly have radial dependence and dependence on the angle from the vertical axis, theta, but no dependence on the rotational angle, phi, about that vertical axis. Thus, we have azimuthal symmetry. The general potential solution expansion in terms of Legendre polynomials is, see the equation.
Let's consider the inner sphere boundary conditions first. See the equation shown. With standard inversion rule, see the equation.
Substituting the indicated sphere potential, see the equation shown.
Thus, we have relations on unknown A sub L and B sub L from the R equals a boundary. See the equation.
Similarly for the R equals B boundary, see the equation shown. Before proceeding, however, let's simplify by choosing to shift the potential by adding a constant, phi prime equals phi minus v divided by 2. For such a choice the boundary conditions are odd functions of the radial coordinate, resulting in an expansion for phi prime that must entirely consist of only odd terms. Choosing new constants to conveniently center on the R equals a boundary we now have, see the equation.
For R equals A, see the equation shown. Using alpha sub L plus beta sub L equals 2L plus 1 over 2 the integral from -1 to 1 of f of xp sub L of cosine theta together with the definition of the potential. See the equation. And we have, see the equation shown. Where the R sub L constants are given by the Rodriguez formula, R sub 1 equals 3 divided by 2. R sub 3 equals -7 divided by 8. R sub 5 equals 11 divided by 16. Let's now consider the R equals B boundary. See the equation. Furthermore, since phi prime of B, theta, equals negative phi prime of A, theta, we must have, see the equation shown. After regrouping,
see the equation. Thus, see the equation shown.
The potential is then, see the equation, where the first three R sub L constants are given above.